I think that the first thing I should emphasize is the fact that the most common reason that owners think they have rear axle gear trouble is noise. Before going any further, let me clarify that statement to some extent. Any time that you have two gears meshing, it's going to produce a certain amount of sound from the teeth coming into contact. It is usually a low decibel sound that is part of the normal running noises such as engine, transmission, and tires. Most drivers do not object to the sound coming from the rear axle unless it gets to the point that it is excessive and objectionable. From here on, I'll refer to rear axle sounds as noise only after they have reached that point. Frequently, rear axle noises can be effectively reduced by readjusting the rear axle gears to mesh properly. And no matter what you've heard, noisy gears will not get quieter with added mileage. They'll either stay noisy or get worse. In most cases, axle gears can be readjusted to reduce excessive noise if they have been operated under normal conditions. However, if the gears have been subjected to severe loads or heavy usage, the chances of getting rid of the noise may become pretty slim. The most important thing to remember is that the hypoid type gears in the rear axle assembly have complicated tooth shapes and must be positioned correctly for the gears to mesh properly. The most positive way to check the axle gear setting is by taking a close look at the gear tooth contact pattern. Some technicians are in the dark when it comes to interpreting a gear tooth contact pattern, so let's see how the pattern is formed before we go into variations of it. I think that the plain straight tooth spur gear will be the best to start with. Because spur gears are straight and aligned with the gear shaft, the meshing teeth are in contact at one point or an imaginary line across the tooth face at any given moment. The initial contact point is near the top of the tooth face, and as the teeth engage, the contact line moves toward the root of the tooth. As the teeth unmesh, the contact line moves back toward the top of the tooth. A rectangular-shaped contact pattern is developed by the rolling action of the in and out movement as the teeth mesh and unmesh. The hypoid-type gear teeth, used only in the rear axle, produce a rolling action along with a sliding action when meshing. This movement creates a contact pattern that moves from the top of the heel to the root of the toe on the face of the tooth. The pattern is roughly oval-shaped and approximately centered on the face of the tooth.
Some of you technicians may not be familiar with or may have heard different terms for the parts of a gear tooth. To avoid confusion, the edges at the inner diameter of the drive gear teeth will be referred to as the toe of the tooth. The outer diameter edges will be called the heel of the tooth. The lower part of the gear tooth will be the root of the gear tooth. The upper edge of the tooth will be referred to as the top of the tooth. And in case you didn't know, the convex side of the tooth is the drive side, and the concave side is the coast side. Go ahead, Matt.
Quiet running gears are assured at the factory before they are installed during production or sent to the dealers as match sets for replacement. The pinion gear is positioned to mesh properly with the drive gear by using a pinion depth adjusting spacer of the right thickness. The gear tooth contact pattern of all gear sets is checked on a machine that is known as a Gleason gear match tester. The gear sets are rotated in their normal operating position at RPMs equivalent to normal driving speeds. Road load can be simulated, and gears can be checked under both drive and coast conditions. Once the gears are set in the chucks in the machine, they are coated evenly with either white, yellow, or red lead. In this sequence of photos, white lead was used to show the pattern with more contrast against the dark gray appearance of new gear teeth. To ensure a clear, distinct pattern, the gears are tested under loads equivalent to some, but not all, driving conditions. Without applying a load, the tooth contact pattern would be a little shorter and slightly blurred or faded. The effect of a load on the gears is achieved by use of a brake device on the machine. Another reason a load is desired is to properly position the tooth contact pattern on the face of the tooth. You see, any time gear teeth come into contact under load, the pattern will move because of normal gear tooth deflection caused by the load. Because of this, the tooth contact pattern will move toward the heel on the drive side of the gear tooth under load. So if the pattern is too close to the heel without a load, it would move further toward the heel under load and more than likely result in a gear set that was objectionably noisy. Now that you've seen what the machine does, let's look at the characteristics of a good tooth contact pattern from a gear set that is meshing properly. We already mentioned that the pattern should be oval-shaped and near the center of the tooth. The pattern on the tooth should be at least 1/2 the length of the drive gear tooth and should have a small area of non-contact at the top and at the root of the tooth. Because of what we discussed about load effects, the pattern should slightly favor the toe of the drive side of the gear tooth.
The drive side of the gear tooth should always be used as the main indicator of proper gear tooth contact patterns. Changing of loads under various driving conditions affects the pattern more on the drive side than on the coast side. As a result, the drive side is less tolerant of pattern errors.
That's right, Tech. Although the coast side of the tooth will also show a distinct pattern, it isn't as critical as the drive side and can cause trouble if it is used to set pinion depth. For demonstration purposes, we're going to use a gear set that can be assembled with a production pinion depth spacer. First, let's see what the pattern looks like without a load. Notice that the pattern is clearly visible on both the drive and coast sides of the gear tooth. But without a load, the tooth contact patterns may be slightly fuzzy and are apt to be rather small. Let's see what happens when a load is applied by the brake. The tooth contact pattern becomes a bit more distinct, and the contact area increases under a simulated operating load. As mentioned earlier, the contact pattern also moves slightly toward the heel on both the drive side and coast side under load. Because of design tolerances, volume production parts that are machined and heat-treated are not all going to be exactly the same. The Gleason machine provides a means to determine the thickness of the pinion depth spacer to compensate for minor variations in dimensions. By moving the drive gear in or out of a pinion gear, the operator can determine how many thousandths thicker or thinner the pinion depth spacer should be when the pinion and drive gear are assembled in the carrier. Let's start by moving the pinion further out of the drive gear. These slides will show tooth contact pattern as it develops when the pinion gear is moved 2/1000th at a time. At 2/1000th, the pattern is starting to move from the center to the heel and up toward the top on the drive side of the tooth. On the coast side of the tooth, the pattern moves in the opposite direction. This slide shows the contact pattern after the pinion has been moved out another 2/1000th. So now it has been moved a total of 4/1000ths out of the drive gear. You can see that the pattern has moved farther from the center on both drive and coast sides. By setting the machine so that the pinion is another 2/1000ths out of the drive gear, the gear tooth pattern has moved to the extreme on the heel and top of the drive side of the tooth. I think that it's pretty plain to see that the edge of the gear tooth is bearing all of the load. If this overload is allowed to continue, the drive and pinion gear will become noisy. Remember, this is what the tooth contact pattern looked like when we started, and this is what it looks like with the pinion moved away from the drive gear 1/6,000th of an inch. Under actual production conditions, the reverse of the previous sequence would take place. If a gear set with an improper pattern were discovered, the machine operator would move the gear in until the proper pattern was produced. Then, he would mark the gear set for proper spacer thickness. I'll elaborate on these markings later. Right now, I'm going to show what happens to the tooth contact pattern when the pinion is moved farther in or toward the toe of the drive gear. Again, we are starting with the right pinion depth setting and the correct tooth contact pattern. Here is the tooth contact pattern with the pinion moved in 2/1000th of an inch. Notice that the pattern has started to move toward the toe end and the root on the drive side of the gear tooth. On the coast side, it has also moved toward the root, but has moved in the opposite direction toward the heel. Because of the cone shape of the pinion gear, the pattern moves up toward the top as the pinion moves out, and down toward the root as the pinion moves in. I think that this slide clearly illustrates these conditions. Getting back to the Gleason, here's what the pattern looks like moved in 4/1000ths of an inch and 6/1000ths of an inch, where the pattern is at the extreme ends of the tooth and very heavy on the root. When the correct tooth contact pattern is determined and the machine operator has established the proper spacer thickness, he marks both the drive gear and the pinion gear with either a plus or minus figure to ensure proper assembly.
I notice there are two other numbers along with the spacer thickness. Do they affect the pinion depth setting?
No, Tech, but they are important. The other symbols are production numbers, and they help identify a matched gear set. Even if a drive and pinion are both marked +2, they will not be a matched set unless the other markings are the same.
What is the size of the standard pinion depth spacer used for assembly if there is no plus or minus figure on the gear set?
First of all gear sets are marked, even if it says -0, where spacer thickness does not have to be increased or decreased. Secondly, there is no standard size pinion depth spacer, and I'll explain that right now. If you had an ideal situation where the carrier, pinion, and bearing were machined right in the middle of the tolerance range, the pinion depth spacer used at assembly would be the size designed for that axle assembly. However, as I mentioned about the pinion gear earlier, production tolerances allow dimensions to vary slightly. The first dimension that determines the thickness of the pinion depth spacer is taken off the carrier housing. The carrier is measured from the center of the cross bores to the bearing shoulder with the bearing cup installed. After the carrier is measured, a spacer thickness corresponding to the carrier dimension is selected. This spacer will give proper pinion depth if the drive and pinion gear set is marked -0, which means further correction of the spacer thickness is not necessary. If the gear set is marked +2, then 0.02 of an inch is subtracted from the spacer thickness determined by the carrier measurement. If the gears are marked -2, then 0.02 is added to the spacer thickness. +2 on the gears means that on the Gleason machine, the pinion gear was set 0.02 out of the drive gear to make the mesh properly. This means that the length of the pinion head is 0.02 longer than exact design dimensions. Therefore, by using a spacer 0.02 thinner, the pinion head will go deeper into the carrier, the correct distance to line up with the drive gear. Just the opposite is true if the gear set is marked -2. This will be demonstrated again in the second part of this session using an assembled axle. A wrong backlash setting is another common cause of rear axle noise. The only way to correctly set the backlash is with a dial indicator. Backlash setting is the distance the drive gear is set away from the pinion, which tells you how deep or shallow the teeth of both gears are meshing. Incorrect backlash can also be simulated on the Gleason machine. The following slides will show what happens to the tooth contact pattern, and you'll see why incorrect backlash can cause a noisy rear axle. This is what the tooth contact pattern looks like when the drive gear is set too close to the pinion gear. The pinion gear teeth mesh very deep in the drive gear, and the tooth contact pattern will have a very sharp line at the root of the tooth. With the drive gear set too far away from the pinion, the teeth are not fully meshed. The contact pattern naturally moves toward the face of the tooth and produces a distinct line across the top edge of the tooth. That's about it for drive and pinion gear adjustments and what kind of tooth contact patterns they produce. Right now, I'd like to show these patterns again and play this tape to demonstrate what effect improper pinion depth can have on rear axle noise. To start, let's go back to the proper pinion depth setting. Here is what the tooth contact pattern looked like, and here is what it sounds like. Notice that the sound is very low decibel and is in the nature of a hum and not harsh. With the pinion moved out of the drive gear 0.02 of an inch, the pattern will look like this and will sound like this. It's light, but the sound has increased and is starting to have a grinding or sharp characteristic. By moving the pinion 2 more thousandths in the same direction, the pattern moves further, and the sound changes to At this point, the sound is increasingly audible and has a definite harshness. With the pinion moved out of the drive gear another 2 thousandths, the pattern has moved to the extreme ends of the gear teeth, and the sound again increases. At this point, the sound of the gears is definitely objectionable and could be classified as noise. To further emphasize how pinion depth can cause rear axle noise, here is a progression of the sound, as the pinion moves out of the axle 0.02 of an inch at a time.
I think it should be stressed that these gear sounds are not exactly the same as the sounds that would be heard inside a car. They merely demonstrate how improper pinion depth setting will create axle noise.